Okay. And so I am happy to be here. I've actually brought one of my students, Jacob. So we will be joining you for dinner. If you have any questions, we'll be thrilled to chat with you afterwards. And then what I want to do today is talk a little bit about some problems that I have done in the past. Interestingly, it is not sharing the screen right now. This is the glory of the 21st century. So let me just close things and reboot, because that's how we always solve problems. So there's a small, like 1 second delay between when I move something here and it shows up over there. So I've almost hit 17 talks at Hampshire College. I'm fast approaching that magic number. All different, yeah. And so in fact, this talk is being done with less than 24 hours notice from when I heard that there was a need for a speaker today. And so I spent more time looking at, well, what talks have I given in the past? Which topics have I missed? And so the last time I gave a version of this talk was actually to my son and 2 of his friends in 9th grade who were learning calculus, and I wanted to show them some applications of calculus. The first time I gave this talk was to the Williams and Mystic program. So this is a multiple avenues, to get into this material. One of the reasons I love coming back here, and I told my wife, of course I'm going, is I've never been places better than Hampshire College for having students interacting with the talks. And so it's just such a joy to be back here in person and not doing this by Zoom. Please speak up, please answer, please ask questions, do not be afraid. When I was a young professor at Williams, I was teaching differential equations, and we don't require linear algebra. And I wanted to use a linear algebra, and I asked the students, how many of you are comfortable with 2x2 matrices? Silence. Is everybody comfortable? Does anybody want a review? Nobody wanted a review. So I'm going to use clickers. And just if you want a review, press 1. If you don't want a review, press 2. I'm not going to tell the results to the class, but I'm just curious. I never said I wouldn't tell other classes. 43% of the students wanted a review of 2x2 matrices. 0% were willing to raise their hands. You would have gotten a lot more out of that. Now, I knew enough to just ignore what people were doing. You get a lot more when you speak up. And so I'm actually mentoring 2 former students from the Hampshire program in research projects right now over the summer. And so if people are interested in pursuing things further, by all means, please talk to me afterwards. If you can't find my email address, then you have not entered the 21st century. There should be enough information here, especially like here on the screen. But you should be able to talk to people in the program to find my address. I've worked with over 600 students over the years. You're always happy to talk to people about ways to apply. Okay, so I'm not going to go through too much of the introduction. How many of you have heard of the butterfly effect and chaos? Okay, good. So great. So you all know that. So there's a lot of stuff from that. A lot of chaos can be linked to extreme sensitivity to initial conditions. A very small change in initial conditions very quickly leads to wildly different behavior. How many of you have studied the pendulum in physics? Okay, where is the equilibrium, or where are equilibria for a pendulum? Okay, so you got to say it out loud. Straight down or straight up. One of them is a stable and one of them is an unstable. We often forget these straight up. If you disturb it ever so slightly, you're going to get wildly different behavior, and you will no longer be close to where you were after a small amount of time. Straight down, if you perturb it ever so slightly, it will stay close. And so one of the big things is trying to understand how sensitive is your system to initial conditions. One of my former students is at a think tank, and he does a lot of work on climate models. And I am not going to talk about the science behind these discussions, but what I will say is that a lot of these models are extremely sensitive to your choice of parameters. And you've got to be very careful when you have models that are very sensitive. How well do you know the parameter? Which methods can you use? Which ones do you have to really spend your time on? All right, so what I want to do is I want to talk about some problems related to calculus, but in such a way as to give you a sense of what do I do with my students. My brother is an engineer, and at times he wants to hit me. Now, partly it's because he's my brother, but also because I'm a theoretical mathematician, and as an engineer, we don't need all this theoretical math stuff. We can just work with things. And as mathematicians, we snicker, and I can see several of you through your masks snickering. Well, no, because what about this really extreme counterexample? He's like, yeah, and that doesn't happen in the real world. So can you define mathematical terms? So one of the biggest problems is to try to figure out, what do you want to study? So can someone define dimension for me, mathematical dimension? And if you can't define it, at least give me examples. Yes.
I'm gonna have examples.
Okay, good.
Length,
Length, width, height. So what are the possible values for dimension? Positive numbers, or non-negative. So could we have something that's zero dimensional? Yes, you could have something that's a point. So can someone give me a mathematical definition of dimension? Okay, go for it.
Okay, I think it depends on the objects that they're working.
Okay. So give me a definition for maybe some nice class of objects. So, if it's too much to describe it in general, let's try to describe it in a specific example.
Well, I guess if we're talking about like spatial dimensions,
Okay.
we can think of it as like how many lines can we draw that crosses together that are, or like how many lines can we draw such that they intersect in a point at which all of them are perpendicular to each other.
Good. So that's a nice working definition. Now, if you use that as your definition, what are you going to get for your possible dimensions?
Natural numbers.
Natural numbers. I think we can have a debate as to whether or not we consider zero a natural number. I don't want to split us into groups like that. We'll have this out at dinner.
It's already happened.
Oh, it's already happened. All right, well, I will not say where I stand on this divided question so early in the talk. I will save that for later. So just for some notation, R, and I have a strong Boston accent, is the set of real numbers. R squared is the set of pairs of real numbers, and so on. And so dilating a set by a factor of R means you rescale every coordinate by a factor of R. And so here is a nice notion of dimension. This is the Hausdorff dimension. How many of you have done chaos have seen this? Excellent. So already we've done something that you haven't seen. So if you take a set in Rn, we dilate by a factor of R, and let's assume that when we do that, we get C copies of the initial set S. Then the dimension D is the number such that R to the D equals C. So whenever you see a definition, what should you immediately try to do? Yeah, test it. So can somebody give me an easy example where we could try to test this definition? Somebody give me an object whose dimension you think you know. Unit square, unit cube. Come on, who wants to be nice to me? A line, thank you, right? Let's start off with, I love this eagerness. Let's go straight to 2 and 3 dimensions, but let's work our way up. How much time do I have to fill up? Right. So let's start off with a line. And so I will choose the number 3. I would have done 17, but to draw 17 things is just going to get really bad as we go down. So I do apologize. So let's take a segment of length 1. We take R equals 3, so we dilate by a factor of 3. And the interval 0, 1 now becomes the interval 0, 3. So we now have 3 copies of our initial set. So we want R to the D equals C. So we get D has to equal 1. This is not a very difficult equation to solve. Building on our success, now what should we do? Go to 2 dimensions. So let's do a square. So we take a 1 by 1 square. We dilate by a factor of 3. And now we get this beautiful 3 by 3 square. And so now we're trying to solve R to the D equals C. So we have 9 copies, 9 equals 3 squared. I could, of course, draw 3 cubed. I could easily do that. If you really want me to, I can try to do 4 dimensions, but it's not going to be pretty. But we can see what's going on here. This definition matches our intuition. And if you think about what's going on locally, if I give you any nice object locally, if it's in 3 dimensions locally, I have a little cube around it. If it's in 2 dimensions locally, I have a little square around it. So this is a really good definition that allows us to try to mathematically work with things. Now, an interesting question is, can you have something that's not an integer? So how many of you have seen the Cantor set? Okay. How many people have not seen the Cantor set? Okay, so I will go through the Cantor set somewhat quickly. So, and again, I'm happy to go into greater detail if people want, The way the Cantor set works is you chop off the middle third and you throw it away. So we start off with the interval 0, 1, and then we throw away the middle third. And now this is the first level. We have now 0 to 1/3, and we have 2/3 to 1. We now throw away the middle third of everything that's left. Oops, I'm just going very slow. And so now we throw away the middle third of what's left. And so now we have 4 intervals. For somebody who hasn't seen the Cantor set, next level, how many things do you think there'll be? 8. And what do you think the length is going to be as you go further and further down? 0. So the length is going to be 0. So this is a set whose dimension should be less than 1. So there's a nice upper bound on the dimension. Can someone give me a lower bound on the dimension? It can be a trivial lower bound. It doesn't have to be impressive. -2. That no, it doesn't impress me, but it works. Can somebody give me a better lower bound than -2? -1. Okay. So can somebody give me the supremum of all these? Yes. So we know the dimension is somewhere between 0 and 1. Okay. Well, what is it? So we need to figure out what do we want to dilate by. And so, again, it gets harder and harder to see these. Could anybody think what we should choose for our dilation factor? 2 is a possibility, but 1/3 is a possibility. I don't like to do division. So instead of doing 1/3, what should I do? 3. I'd much rather multiply. And the reason to multiply by 3 is now this part over here is going to expand and become the whole thing. So if I dilate by a factor of 3, how many copies of the Cantor set do I get? So this part over here expands and becomes everything. So this part from 0 to 1/3 fills out from 0 to 1. This nothingness from 1/3 to 2/3 expands and becomes nothing from 1 to 2. And then this part from 2/3 to 1 expands and becomes another copy from 2 to 3. So how many copies of the Cantor set do I get if I take r equals 3? I get 2. And so if r equals 3, I get 2 copies. So the dimension satisfies 3 to the d equals 2, or d is the log of 2 base 3, or about 0.63093. It's less than 1, greater than 0, it makes sense. Okay, so we now have our first example of a set that has a non-integer dimension. And we'll return to this. I'm not even going to ask how many of you have seen Pascal's triangle. By now, I assume everybody has seen it, lived it, loved it, right? Lots of things you can do. How many of you have seen the connections between Pascal's triangle and chaos? Okay. So we're going to modify Pascal's triangle. We have spent a tremendous amount of our budget on COVID tests and vaccines and all this stuff. We don't have enough money to draw and label all the integers in Pascal's triangle. So instead, what we're going to do is we're going to just put a dot if it's odd and nothing if it's even. Huge budget cuts. And we're going to look and see, what does Pascal's triangle look like if we look at the entries mod 2? Well, if we look at just the first row, it's just a dot. If we look at the first 4 rows, the only even number is in the 3rd row, the 1, 2, 1. If we go to the 8th level, we have 2 things that are missing. And so you can keep going on and on and on. Okay? So every now and then you discover that something that should have been done in the world wasn't. So nobody had actually written a program and publicly posted on the web that I could find that would just show Pascal's triangle as you just add more and more rows. So, I was talking about budget cuts. I had requested, and I've requested for years, an infinitely long screen. And, I'm still waiting. It's been, well over a decade. So what you do is you always compress and say, I'm always going to display in a fixed amount. And so let's see if I can get this to work. Professor at Williams College, and I want to talk to you today about some fascinating properties of Pascal's triangle. The image stays on the same size. All right, so over here, I'm at the first row. I'm going to keep adding rows. So hopefully you can see the dots coming in as we go more and more. A structure emerging. looks a
And what
little bit
you
like
can
a
see
superstar destroyer. from
is
Star
what's
Wars.
actually known as a fractal. And so you see this piece over here repeats and is here and here. Then this bigger block repeats and is here and here.
And so absolutely wonderful. Let's see if this will switch it back here. Perfect. So I initially did it because it was a little bit easier in Mathematica to have the triangle rotated 90 degrees. This is a better video where it's now going from top down. But you can see that as you keep adding more and more rows, you have this beautiful fractal structure, and it's very similar to the Cantor set. And so in the Cantor set, we removed the middle third. What we can do now is if I have an equilateral triangle, I can take the midpoints of each side, and that gives me 4 triangles, and I throw away the middle, and I can keep iterating. And it turns out that this is exactly what you get when you look at Pascal's triangle. So what is its dimension? So somebody has to tell me, what should I rescale by? Yes, 2. Excellent. If I rescale by 2, this interval 0 to 1/2 becomes 0 to 1. So this thing over here becomes a full copy. So how many copies will I get if I rescale by 2? 3. What bounds can you give me on the dimension before I even do the calculation? Upper and lower bounds? Infinity, okay. And you're probably one of the people who has the wrong classification for 0. So give me semi-reasonable bounds. 1 is a lower bound, because we always have the outer side, good. And an upper bound, yeah, this should not be a 3-dimensional object or something greater than 2. So it should be something between 1 and 2. And so since when I equals 2, we get 3 copies, we get 2 to the d equals 3. So we get d is the log of 3 base 2, or about 1.58. And again, this fits beautifully with our theory. So this notion of dimension is wonderful. And it turns out stuff like this actually occurs in real life. So whenever you are doing math or seeing math, you should always be thinking, how can you generalize? So what I want to do now is I want you to just suggest some generalizations that you could do. There's no wrong answer. Just what else could you study? What else could we look at? So you could look at different kind of transformation. Excellent. Let's keep it on Pascal's triangle. And Pascal's triangle, we looked at it mod 2, even and odd. What else could we do? Mod 3, what else? So what would you do after 3? 4, which is now 2 squared. What else could you do? 5. So, does it depend on how the number factors? Does it depend if the number is prime? You could also look at a pyramidal version of Pascal's triangle, a 3-dimensional version, multinomial coefficients. And you could start asking, what happens there? So whenever you have a problem, you always want to ask, how can you generalize? So this is looking at things mod 3, mod 4. It's amazing what you can find on the web, mod 5. And then, again, my advice to you is always to ask new questions. So one of the reasons why I have published so many papers with students is we're always asking questions. And so I was teaching a class at Williams on L functions and sphere packing. We were talking about the notion of dimension. And so I asked my students, can any real number be a fractal dimension? Can anybody give me at least a partial answer to this? So 0 would be a point. So what can you give me a partial answer to which R's can be fractal dimensions? So negative numbers should not be acceptable, good. Well, you could have maybe we'll put that 0 in the debate that's going on with everything else. Do you know anything else about which R's could be fractal dimensions? All natural numbers. What else? That aren't 0. All positive naturals. Good. What else? There's at least 2 other numbers you should be able to tell me right now. Yeah, whatever we just saw. Right, we know those work, right? And then it turns out no matter what positive real number I give you, I can always find a fractal set that has that as its dimension. So as a nice exercise, try to see if you can prove that no matter what number I give you, and then what's your construction? And so this is what I mean is when you hear a talk, always try to think, how can I push it forward? What new things can I do? Does it matter if somebody else has done it? No.
So does something very interesting happen when the dimension is like pi or e?
I don't know. And I mean, that would be an interesting question to see if there are certain critical values where interesting behavior kicks in. And a lot of times answers depend on certain structure. There's a notion of how irrational an irrational number is. Different irrational numbers have different properties. Does anybody know which irrational number is in some sense the most irrational of all irrationals? It's not pi, it's not e. You might actually think it's a nice irrational number. It doesn't involve the square root of 2, it involves the square root of 5. The golden ratio, the golden mean. And so there is an international association of Fibonacci numbers. There is a board. My greatest achievement to date is that I extended the number of members of the board from 12 to 13. So look, either we make Fibonacci an honorary emeritus member, or we just add someone else, but we shouldn't have 12 members of the Fibonacci board. So I am happy to say I am the president-elect of the Fibonacci Association. So if you have any Fibonacci needs, please let me know. Our numbers are available. We do birthdays, bar mitzvahs, weddings, math research. So we just had a conference at the University of Sarajevo. The next one is going to be probably in Los Angeles in 2 years. And so we've had lots of students present stuff. And so if people are interested, let me know. I've got lots of students working on stuff like this. In some sense, the golden mean is the most irrational of all numbers. Yes. Okay. And so what I want you to always be thinking about is what questions can I ask? And you can just get in a habit of almost anything. How can I generalize this? How can I push it further? What techniques are being used? What parts of these are truly needed? All right. I'm going to skip the coastline stuff. And I'm going to go to a little bit of chaos. So much of math is about solving equations. Now, as you get older, I do a lot of applied math. I wish I could solve equations. The equations get far too complicated to solve. And it's even worse than that. We don't even know what we're supposed to be solving. So who here has ever flown on an airplane? Who here has ever had issues flying on an airplane? Oh, I was surprised that not every hand was up for both questions. So the airlines have to try to figure out what is the demand going to be between two cities 4 months from now, with a lot of other constraints. It is a very difficult, challenging problem to figure out how to assign planes and routes. And so when you're trying to optimize various things, it's a real challenge because not only are the problems you're trying to solve difficult, you don't even know the values of the coefficients going into it. I sometimes give a talk, how many people have seen linear algebra and eigenvalues? It's for those of you who've seen it. In some work I do, we need to find eigenvalues of matrices. There's only two twists that make this problem hard. The first is the matrices are infinite by infinite. And if you thought that was bad, the second one is we don't know any of the entries. And so you can imagine how challenging that, and this is what we have to do. We want to figure out what should the airlines do when we don't even know what the demands are. Well, we try to estimate the demands. So for now, we will assume we have simple equations where we know what the coefficients are. Out of curiosity, how many people have done the drowning swimmer problem in calculus? Drowning swimmer. So you have somebody who's swimming in the water and they're drowning, and you have a lifeguard on shore. What's the lifeguard's goal? To get there as fast as possible. And if you know physics, the path they take is they don't run straight to the drowning swimmer because the lifeguard moves faster on land than on water. And so they go at some angle. They don't go straight underneath because they don't go, infinitely fast on land. And they go at some angle and then they bend. And it's exactly the bending of light passing between two different media. It's the same equations. When you try to solve this, you actually get a quartic, a degree 4 polynomial that you have to solve. This very simple problem leads to some complicated math. So there's a lot of good math behind solving equations. If I give you a linear equation, ax plus b equals 0, this is not a challenge, especially in this building. All right. If I give you a quadratic, everybody I think can give me the sing song. Yes. Right. Yeah, exactly. What about cubic? Who can give me the cubic? In the old days of Hampshire College before the pandemic. So here's the cubic. And this is all 3 roots. Now, the first thing you learn, how many people know logarithms? How many know W logarithms without loss of generality? It's the most important logarithm. So if I'm looking at this equation without loss of generality, what can you say about A? Without loss of generality, we may assume A equals 1. If A is not equal to 1, we can rescale it. The only difficulty is if A equals 0. If A equals 0, it's a quadratic. Then without loss of generality, we can actually translate and we can assume B equals 0. So it's a nice exercise you can show. You can translate to the case A equals 1, B equals 0. So the equations become a little bit better. Here's the quartic. This is just one root. I had to reduce the font size a little bit to get everything there. Okay. I don't understand why people haven't memorized these. Okay. Now, there is no closed form expression for polynomials of degree 5 or higher. Absolutely beautiful result in higher mathematics, that you cannot write down a formula that will give you the roots. Now, once I tell you the polynomial's coefficients, it does specify the roots, but I can't write it as polynomials and radicals and sums and products and differences and all that stuff. All right. So let's try to find roots numerically. Let's come up with some procedures. So here we have a continuous function. It's negative near 0. It's positive near 1. What can you tell me? It crosses somewhere between. Are there any Star Trek fans here? Do people at least know what the transporter is in Star Trek? It beams you from one place to another instantaneously, or within a few seconds. The reason they added a transporter in Star Trek was originally they were going to have a shuttlecraft to take them to the planet, but they didn't have the budget to build the shuttle. So what if we just push a button and then all of a sudden we change scenes and they're now over here? And how much would that cost? We could afford that. Yes, let's do that. So you don't have that. You don't have the function discontinuously going from here because we assumed it was continuous. So we know there has to be a point of intersection somewhere in between. Is someone here willing to somewhat divulge either their birthday or a randomly chosen day in the year? Okay, so don't say it out loud.
April 17th.
Okay, thank you for not saying it out loud. Is there somebody else who is willing to? Okay, but don't say it out loud. It would be really interesting if it was that number. So I'm going to try to guess, and I'm going to guess your birthday in 10 questions. And if I'm wrong, you have to say earlier or later. January 1st, January 2nd, January 3rd, January 4th. I'm not going to do it, am I? No, okay. Let me try a new strategy. July 1st. Now you have to say earlier or later. Later. So with that one question, I eliminated half the possibilities. Now what do I do next?
Go in the middle again.
Go to the middle again. So July, August, September. I'll go with September 31st because August and July both have 31 days. So is it September 31st? Later. So now again, I go halfway in between. So every guess cuts in half my uncertainty. So 2 to the 10th is 1,024. So I can get your birthday in 10 questions like this. This is divide and conquer. I think we were talking earlier about methods to try to count how many people are in here. Divide and conquer is absolutely wonderful. I'll get in 10 guesses. So this is just putting it in math speak. If you have a continuous function, look at its values at the left and the right endpoints, then look at the middle. If it happens to be 0 at the middle, yay, we win. If not, then look to see where is it negative positive or positive negative, and then that's where you split the next one. And then lather, rinse, repeat, shampoo mathematics. So for example, if f of 0 is -1, f of 1 is 3, we look at f of a half if it's 2. So I know there's got to be somewhere between 0 and a half. If I then look at f at a quarter, that's -0.4. So it's somewhere between 0.25 and 0.5. So let's take x squared minus 3. So what value of x satisfies x squared minus 3 equals 0? Actually, I kind of misled you. What values? So what values of x satisfy x squared minus 3 equals 0? Root 3 and negative root 3. So we'll aim for the positive root. Okay, and so this is divide and conquer. And with 10 iterations, I now have the root is somewhere between 1.7304, 1.7324, Root 3 is about 1.73205. That's not terrible. Every 10 iterations of divide and conquer gives you another 3 digits of decimal accuracy. Why? Well, 10 to the 3, 1,000, is almost 2 to the 10. 2 to the 10 is 1,024. So every 10 iterations is approximately, if I do that, each one gives me a half, a half, a half, a half. That's like 1 over 1,000. So that's about 3 more decimal digits. It's a little bit better. So if you want 6 digits of accuracy, how many times would you have to do this? 20. What if you want 12 digits of accuracy? So how many for 12 digits? 40. That's a lot. But all you have to do is evaluate the function well enough to know, is it positive, negative, or 0? You just have to evaluate the sign. And you can do all of this with rational numbers, so this can be done. It's not too bad. 40, however, is a lot. So let me teach you a better way. How many of you have seen Newton's method? Okay, a lot, but not everyone. So we're going to use point slope. There's lots of ways of writing a line. Y minus y naught equals mx minus m naught, or just moving things over. If I give you 2 points determine a line. If I move over 1 unit in x, the slope tells me then how much I change in y. And so we take a lot of calculus classes. Hopefully they've told you why. One of the reasons is functions are complicated. The nicest function we can work with is a straight line. Wouldn't it be wonderful if every function were a straight line? Well, locally, every function is a straight line, at least if the function is nice. So calculus, in some sense, is how can I approximate everything locally with a straight line and just keep track of the errors and whatnot. So what we're going to do is we're going to use the tangent line. And so, for instance, here is my function f of x is 2x cubed minus 3x plus 1. I take the derivative and I approximate the function locally with that tangent line. And for a decent amount of movement in x, you really can't tell the difference between the function and the straight line. Here is the function cosine of x. And again, there's a good window near x equals 4 where I can't tell the difference between the function and the straight line. So how does this help? So here's Newton's method. And this is what converted me from, I was torn between being a math and physics person to I'm a math person. I still majored in physics, but this was when I decided, no, I got to do math. So what you do is take a continuous and differentiable function. Is there anybody here who has not done calculus? Okay, so if you haven't done calculus, we can talk a little bit over dinner. It's basically a way to tell you how fast is the function changing at a point. Okay, so there is a rule. Given a function, f of x, I can tell you a new function, which we call f prime. We call it f prime to highlight the fact that it's related to your initial function, that will tell you how quickly is the function changing, instantaneously. If you want, imagine f of x is how far you are from home. So you're looking at the tripometer, the odometer to see how far you've traveled, and then f prime of x is your speed. And the idea is, if your function is nice, there should be a way to get your speed if you know your distance. And all we need to know today, and we can prove this over dinner, is that if I give you the function x to the n, its derivative is nx to the n minus 1. So if I give you the function x squared, its derivative is 2x. If I give you x cubed, somebody who hasn't done calculus, what would be the derivative of x cubed? 3x squared, perfect. And so what Newton's method says is take a continuous differentiable function, draw the tangent line to the curve at a point xn, calculate the tangent line, see where the tangent line hits the x-axis, and call that intersection your new point xn plus 1. And this will be a sequence of points that approximates where your function vanishes. And you can actually write this down in closed form, and you get the next approximation, xn plus 1, is your previous minus f of xn over f prime of xn. So for example, here's my function. Here's my initial point x naught. I draw the tangent line. Essentially, the tangent line is, imagine there's no acceleration, so your speed is constant. And so I know where I am. I know how fast I'm going at that instant, and I assume I always travel at that speed, no acceleration. I see, where do I hit? I hit down here at x1. Who here has ever read the instructions on a bottle of shampoo? I am terrified right now with how few hands are going up. All right, so later tonight, please read the instructions on shampoo. What do the instructions on shampoo tell you to do? Okay, it's more than just repeat. Lather, rinse, repeat. You can't just repeat without doing something, right? So lather, rinse, repeat. So you just keep lather, rinse, repeat. Well, we now do it again. We now find what's the tangent line at that point and see where it goes. And we just keep doing this and doing this and doing this. And the hope is that this will converge to the root. And so it turns out if we do f of x is x squared minus 3, the function we were looking at before, when you go through and do the algebra, you get the next term in your approximation is 1/2 the previous term plus 3 over the previous term. So when you're looking at this, you always want to ask, is this formula reasonable? Can anybody think of an interesting value to put in for xn? I'm sorry? So if you put in 0, it's going to blow up. So it's an interesting value to put in. And 0 is right between which two numbers? Yeah. So which are the two numbers that really matter, right? We'll see that later. All right, so it blows up at 0. Give me another number that might be interesting to put in. Square root of 3. If we put in root 3, we get root 3 plus 3 over root, 3 over root 3 is root 3. 2 root 3 divided by 2 is root 3. This is what's known as a fixed point. If you happen to hit the root, good, you stay there. It would be terrible if you found the answer and then you kept moving away. If you take something like xn equals 100, well, 100 plus 3 over 100 is basically 100. This drops down to 50. Then you put in 50 plus this is basically 0, drops down to 25. So it looks like if you start very high above root 3, you're going to quickly fall down and hopefully you'll converge to root 3. And so what we can do is we can go through, I'm not going to go through and do all the algebra, but if you just write down the equation of the tangent line, if you solve for the equation of the tangent line and you solve, at the end of the day, you get the formula that I claimed. Okay, and here we go. It's 1/2 xn plus 3 over xn. This is a beautiful, simple formula. And if you start off with a rational guess, all of your subsequent guesses are rational. These are very easy to work with. So the next few moments is my attempt to show you the beauty of mathematics. If I fail, I will not sleep well tonight. This is the moment that converted me to mathematics. Let's see how well it does. So this is the difference between pure math and applied math. We have this wonderful theory. Can I see how well does it work in the real world? Does everyone agree that for the square root of 3, 2 is not an unreasonably great initial guess? I'm not stacking things in my favor. Okay, so let's plug in 2 to our formula. We get 7/4, so 1.75. Square root of 3 is 1.73205. With just one iteration, we're at 1.75. That's not bad. What should we do? Or lather, rinse, repeat. We're going to work on hygiene here. All right, now we get 9756, 1.73214. It's 1.73205. I'm off by 0.00009, I think, roughly, something like that. That's not bad. What should we do? Again, x3, 1.732050810, 1.732050876. I'm off by 0.000000024. That's not bad. What should we do? Yeah, I'm running out of space here, so I'm going to just write down on the bottom. Guess. I can write it as a rational number, and you can look exactly how far you have to go before you finally see a difference. Okay. Now, what did we do before we did Newton's method?
Solve it with a quadratic.
Well, no. This was but what else did we do? Divide and conquer. Every 10 iterations got you 3 digits. You want 12 digits, 40 iterations. Look at how many digits we're getting with just 5 iterations. Newton's method, every iteration doubles your number of decimal digits. Incredible how much better this is. So let's play some games. So let's take the polynomial x squared minus 1. This is very easy to factor. And so I'm going to color the roots. -1 will be colored red, 1 will be colored blue. And I'm going to apply Newton's method. And if you converge to the blue root, I'll color you blue. If you converge to the red root, I'll color you red. If you don't converge to anything, I'll color you purple. All right? Can anybody tell me who's going to converge to the red root? Negative numbers. And in fact, you can see that if I put in a negative number, I stay negative. I put in a positive number, I stay positive. That doesn't mean that you're going to converge, but at least I know if I start off negative, I can't converge to the positive. So we have one candidate that's still open, which is the open candidate. And then what do you think happens to 0? Yeah, 0 doesn't play. Okay, and so this is the coloring. So this game was not that exciting. So instead of using a quadratic, what should we do? A cubic. So I happen to have one already on the slides. This is a wonderful coincidence. Let's look at x cubed minus 1. Now we can actually factor this, because if you look at this, can somebody give me a root of x cubed minus 1? 1. So we can do polynomial long division. Yay! Or you can use a software program like Mathematica and do either factor or polynomial long division there, because this is the 21st century. And so when you factor it, you get 3 roots are at 1, negative 1/2 plus I root 3 over 2, and negative 1/2 minus I root 3 over 2. So I'm going to put them in the complex plane. And now I'm going to apply Newton's method. I have 3 points colored red, blue, and green. Can somebody tell me in a nice way, which points do you think converge to blue, which to red, which to green? Well, okay, so if you know the answer, don't say it. If you know the answer, don't say it. Can somebody give me what you think it might be? Yes. Okay, so let's trisect the origin. So now can you tell me, at least morally, which roots do you want to converge to red? I'm sorry? So which one should converge to red? There's a nice way in English to say what the answer is, or at least what the answer should be. So raise your hand. Who wants to try to say it nicely? Give me a nice description of the condition that if you satisfy this condition, we hope you will converge to red. Yeah, there's a nice description of what we hope to happen. Not what happens, what we hope to happen. Yes. Good. Or another way of saying it is, if you are near red or closest to red, right? You're very close to what you say. You converge to whichever one you're closest to. No. And when you see this, this should not be happening. And so, this is chaos. This is a beautiful fractal. And so over here, wait a minute, I'm closest to green by just a little bit over red, but I'm going to converge to blue? That doesn't seem right. Now, when you go to the web, you can get lots of wonderful videos, and sometimes they have cheesy, sometimes they don't have cheesy soundtracks. Let's see which one this is. So this should be zooming in on z cubed minus 1. So this one does not have the cheesy music. I noticed that it has things oriented slightly differently than it flipped the red and the green. The red should absolutely be on top and the green on the bottom of its side. And then it's just, look at what's happening over there as we get closer to the center. What kind of shape does that look like? Yeah, it looks hexagonal. I think hexagonal is a word. So the darkness is the difficulty in evaluating what's going on. And so when you have stuff like this, when you have fractals, we have to actually talk about fast ways to evaluate polynomials. So, we started today by talking about dimension and talking about, fractal shapes. Here is a beautiful fractal shape that you can start looking at. And there's a lot of questions you can ask about this. So some of my students have been doing research questions related to.
We are farmers.
Oh.
Hey, this is Presh Talwalkar.
Interesting. Okay. So I am from Western Mass, where Shays Rebellion still lives on all these years later. The farmers have come back. Excellent. And so you have incredible difficulty in figuring out what's going on at these points. And these calculations become incredibly difficult. You need tremendous precision to see what's going on. But you can start asking lots of research questions. What can you say about the number of bumps? What quantities might you want to ask about these bumps? So hopefully they are the color they are. What else might you want to ask about these bumps? What is the dimension? So I'm glad you didn't say, what's the area? Because when you say, what's the area, what are you assuming? That it has an area, right? We don't even know if there's an area. I might be interested in maybe some kind of relative ratio between these quantities. But if they're not areas, I don't know if looking at the ratio of their squares or their square roots is the right thing to look at. So maybe I'll look at ratios of raising them to a certain power related to the dimension. And is there a nice relation between the dimensions of these or the sizes of these and some general notion of what I mean by size? And so there's a lot of great research questions that you can get into. Now, to solve these requires a lot of advanced mathematics. But you see that it all started from a really simple question. What is dimension? This is something that we just work with without really thinking about. We know what dimension is. Well, if we stop and think, well, what actually do we mean by what is dimension? And then try to write down something mathematical that we can then work with, it opens us up to a lot of interesting questions. There are more than one ways to calculate things. Theoretically, divide and conquer is in some sense better than Newton's method. Divide and conquer only needs the function to be continuous. What does Newton's method need? So is there anybody here who has not seen continuous functions? See, everybody's seen continuous functions. Differentiable functions, I now need calculus. So Newton's method requires more. Well, not surprisingly, the more you have at your disposal, you should be able to do better. I'm not going to try to do all mathematics with your both hands tied behind my back, hopping on one foot with loud music blaring, right? I want to use the theorems that I have. And so by going in far in mathematics, how can I bring these theorems to bear on what I'm doing? So anyways, this is what I wanted to cover for today. So I'm happy to stick around and answer questions. I'll just stop the recording.